The role of structural engineers in disaster recovery. Introduction. When disaster strikes, the immediate focus is often on rescue and relief. But what happens next? How do communities rebuild safer, stronger, and smarter? That's where structural engineers play a vital role. Today, we'll explore how these unsung heroes help in disaster recovery, shaping resilient communities after the unthinkable happens. What do structural engineers do in disaster recovery? Structural engineers assess, plan, and rebuild. After an earthquake, hurricane, or other disaster, their first task is damage assessment. They inspect buildings, bridges, and other infrastructure to determine what's safe and what needs repair or replacement. For example, after an earthquake, engineers evaluate if damaged buildings can be retrofitted to withstand future tremors, or if they must be demolished. Their expertise ensures that decisions are based on safety and sustainability. Steps in disaster recovery. 1. Damage assessment. Structural engineers use advanced tools like drones, sensors, and computer modeling to quickly evaluate large-scale damage. They prioritize which structures need immediate attention, ensuring resources are allocated effectively. 2. Stabilization and temporary repairs. To prevent further damage, engineers design temporary supports for buildings and bridges. For instance, they might stabilize a cracked hospital so it can keep operating during recovery. 3. Redesign and reconstruction. Here's where structural engineers shine. They don't just rebuild, they redesign for resilience. New structures incorporate improved materials, modern techniques, and lessons learned from the disaster. This minimizes risks from future events. 4. Community collaboration. Structural engineers work closely with architects, city planners, and emergency managers to align reconstruction efforts with long-term community goals. For example, they may design flood-resistant homes in areas prone to hurricanes or earthquake-resistant schools in seismic zones. Real-world examples. One example is New Orleans after Hurricane Katrina. Structural engineers helped redesign levees and flood walls to prevent another catastrophic failure. Similarly, after the 2011 earthquake in Christchurch, New Zealand, engineers led efforts to retrofit historic buildings and design safer infrastructure for future resilience. Challenges engineers face. The work is not without challenges. Limited resources, time constraints, and political pressures can complicate recovery efforts. Yet, structural engineers persevere, driven by their commitment to public safety and sustainable rebuilding. Structural engineers are the backbone of disaster recovery. Their work doesn't just restore what was lost, it lays the foundation for a safer, more resilient future. By assessing damage, stabilizing structures, and designing with disaster resilience in mind, they ensure communities can bounce back stronger than before. Thank you for exploring the critical role of structural engineers in disaster recovery. If you found this insightful, like, share, and subscribe for more on the hidden heroes shaping our world. Bridges are vital lifelines in our infrastructure, but their durability and performance hinge on one critical component: the bridge deck. Over time, the materials used in bridge decks have evolved dramatically, driven by the need for longer lifespans, greater load capacities, and lower maintenance costs. Today, let's explore the latest innovations in bridge deck materials that are revolutionizing how we build and maintain these essential structures. What makes bridge deck materials important? The bridge deck is the surface that directly supports vehicles, pedestrians, and other loads. It's exposed to constant stress from traffic, weather, and environmental factors. Choosing the right material can mean the difference between a bridge that lasts decades with minimal repairs and one that requires frequent, costly maintenance. Traditional materials like concrete and steel have served us well, but advancements in technology are introducing more efficient, sustainable alternatives. Key innovations in bridge deck materials. 1. Ultra-high-performance concrete, UHPC. UHPC is a game-changer in bridge construction. This material is significantly stronger and more durable than traditional concrete, with superior resistance to cracking and water infiltration. Its high tensile strength allows for thinner, lighter decks without compromising structural integrity. Additionally, its longevity reduces maintenance costs, making it a popular choice for modern bridge projects. 2. Fiber-reinforced polymers (FRP). FRP composites are lightweight, corrosion-resistant, and incredibly strong. These materials are especially effective in environments with high humidity, salt exposure, or extreme temperatures. FRP decks are easy to install, as their lightweight nature reduces the need for heavy lifting equipment. Moreover, their low maintenance requirements make them ideal for remote or hard-to-access bridges. 3. High-performance steel. Advancements in steel alloys have led to materials with greater strength, ductility, and corrosion resistance. Weathering steel, for example, forms a protective oxide layer that eliminates the need for paint or coatings, reducing maintenance over time. This innovation is particularly valuable for bridges in regions prone to harsh weather conditions. 4. Recycled and sustainable materials. Sustainability is a growing concern in construction. Bridge decks are now incorporating recycled materials like fly ash, slag, and recycled polymers to reduce their environmental footprint. Some projects even use bio-based composites, which combine natural fibers with resins for an eco-friendly, high-performance alternative. These materials align with the global push for greener infrastructure, tools, and techniques enhancing material performance. In addition to new materials, innovations in testing and monitoring have improved bridge deck performance. Advanced sensors embedded in decks can monitor stress, temperature, and vibrations in real time, providing valuable data to engineers. Combined with high-tech materials, these tools ensure that bridge decks meet modern demands for safety and reliability. Conclusion: the bridge deck materials of today represent the intersection of engineering ingenuity and sustainability. From ultra-high-performance concrete to fiber-reinforced polymers, these innovations are paving the way for stronger, more durable, and eco-friendly bridges. Whether it's reducing maintenance costs, improving load capacity, or addressing environmental concerns, these materials are shaping the future of bridge design. Thank you for listening, and remember, innovation is the foundation of lasting infrastructure. The role of civil engineers in urban resilience. Civil engineers play a critical role in building cities that not only thrive today, but also withstand the challenges of tomorrow. Urban resilience is about preparing cities to face natural disasters, climate change, and rapid urbanization while ensuring the safety, sustainability, and well-being of their communities. So, how do civil engineers contribute to this vision? Understanding urban resilience. Urban resilience means a city can absorb, recover from, and adapt to adverse events like floods, earthquakes, and heat waves. Civil engineers are central to this process because they design and maintain the infrastructure that makes cities functional and livable. From roads and bridges to water systems and power grids, engineers are responsible for ensuring these systems remain operational even under extreme conditions. Planning for resilience. Civil engineers begin by assessing risks unique to a city. For example, coastal cities may prioritize flood defenses, while earthquake-prone regions need structures that can withstand seismic forces. Engineers use advanced modeling tools to predict potential hazards and design infrastructure that minimizes vulnerability. This proactive approach is essential for preventing catastrophic failures. Innovative design solutions. Modern civil engineering focuses on creating structures that are not only robust, but also adaptable. Flood-resistant infrastructure. Engineers design levees, drainage systems, and permeable surfaces to manage stormwater effectively. Seismic-resilient buildings. Advanced materials and shock-absorbing foundations help buildings endure earthquakes. Sustainable materials. The use of eco-friendly materials reduces environmental impact and improves long-term resilience. Civil engineers also integrate smart technology into cities. Sensors embedded in bridges, roads, and buildings provide real-time data to monitor conditions and detect potential issues early. Collaboration for resilience. Civil engineers don't work alone. Urban resilience requires collaboration between engineers, architects, policymakers, and communities. By working with governments and urban planners, engineers help create zoning laws and building codes that reduce risks. Engaging with communities ensures that designs meet real-world needs and priorities. Responding to disasters. When disasters strike, Civil engineers are often the first to act. They assess damage, restore critical infrastructure, and rebuild with resilience in mind. For example, after a flood, they might redesign drainage systems to prevent future flooding or elevate buildings in vulnerable areas. Looking ahead, as climate change intensifies and cities grow, the role of civil engineers in urban resilience becomes even more vital. Their expertise ensures that cities are not just places to live, but places where people can thrive despite the challenges of an uncertain future. Civil engineers are the backbone of resilient cities, blending innovation, science, and practical solutions to protect and empower urban communities. Their work is a testament to how engineering can transform challenges into opportunities for a sustainable and resilient world. Thank you for listening. If you found this insightful, share your thoughts or questions below, and stay tuned for more explorations into the engineering world.